Metals shape our modern life. They support our buildings, bring us electricity, move materials and products, and bring us life-giving water. And nearly everywhere metal is used, corrosion can be found. The same natural processes at work on this old car are slowly and steadily eating away at our infrastructure. It's a costly problem. It's estimated that corrosion costs drinking water and sewer systems $36 billion a year in the United States alone. For water utilities, corrosion causes premature failure of system components, which leads to increased operating expenses. Water utilities by nature are particularly vulnerable to corrosion. Metal can be found throughout water systems, treatment plant equipment, pumps, valves, storage tanks, and pipe. The distribution system is often a utility's largest investment, and miles of buried pipe are a utility's greatest liability for corrosion. This video focuses on external corrosion in water utility distribution systems. It will discuss how corrosion works, how to evaluate corrosion potential, methods utilities use to prevent or slow corrosion, and operational considerations when working with pipe and fittings in the field. To learn how to control corrosion, it's important to understand how the process works. When metals are mined, they are generally found as oxides. By adding energy in the refining process, metals become more useful for manufacturing, but also more reactive. Corrosion is simply the process of refined metal reverting back to their stable oxidized state. There are several processes by which corrosion occurs. Two types most relevant to water utilities are galvanic and electrolytic corrosion. Galvanic corrosion is the process harnessed to make an electric battery. There's some chemistry at work, but the basic process can be demonstrated without it. A galvanic cell requires an anode, a cathode, an electrolyte, and an electronic path. An electric current is generated where the anode gives up electrons that flow through the electronic path to the cathode. The anode experiences corrosion, while the cathode does not. It's important to note that the flow of electrical current is opposite the direction that electrons are traveling. A galvanic cell can also be created with a single metal or alloy immersed in a non-uniform electrolyte. Again, corrosion occurs at the anode. In a single piece of metal, the metal itself becomes the electronic path. Galvanic cells can easily be found in a water distribution system. For example, this valve is made of several types of metals. In the absence of a protective coating, a galvanic cell can develop and corrosion will occur at the anode. Pipes can also form galvanic cells. Surrounding soil containing water forms the electrolyte. Variances in the soil or pipe composition can create electric flow and corrosion at the anode.